second talk of the day by Chris Frantz, who is a site reliability engineer at Google OpenTitan project. Chris will be revealing exclusive technical details about the Google OpenTitan, a project used by millions around the globe. His talk title is Secure Builds for Secure Software. I believe this project was also recently mentioned by Colin in his keynote today. So yeah, over to you, Chris.
All right. Oops. I am Chris
Yes, we can see your screen.
Okay, can you hear me?
Absolutely, we can hear you as well.
Okay, good. I am Chris Frantz. I'm the software lead for the OpenTitan project, and my talk is about how to securely build software for your secure devices. So I'll give a brief introduction to the OpenTitan project and kind of what the problem is that we're trying to solve with our software builds, why specifically OpenTitan cares, and how OpenTitan is going to get to a solution that solves the problems that would be laid out in the problem statement. So let's start with the introduction to OpenTitan. So the OpenTitan project is an open source hardware project that is focused on building a high quality, transparent, and vendor agnostic secure silicon root of trust. Open source nature of this project allows anyone in the larger community, and I think that really means anyone, to evaluate and audit the security properties of the design. So just as a quick inventory of what's in the chip, there's a CPU, ROM, flash, RAM, and a bunch of internal peripherals that assist with the operations that a typical root of trust chip would do, such as key derivation or hashing or cryptography. And as Colin alluded to in his presentation, there are quite a few interesting blocks inside, like our AES accelerator and so forth. The design of the OpenTitan chip is compatible with FIPS and Common Criteria certification. So part of the focus on being able to build the software is sort of centered around what do we need to do to make certification easier. So a little bit more background. Although the design is for hardware, the trust rooted in the hardware is really only valuable if the chip can securely boot the software stack. So in OpenTitan's terminology, there are two kinds of code that run in the chip. There's something called creator code and owner code. The creator code is effectively the ROM, and so this is the code that is responsible for securely booting the chip, initializing the internal hardware IP blocks, managing owner secrets, and then securely handing off execution to a validated owner code. The creator code consists both of the Mask ROM and then something that we refer to as the ROM Extension, which is located in Flash. Both of these artifacts are built solely from open code that's in our repository, and their transparency and auditability are what guarantee the boot time security properties of the chip, or guarantee them to the owner. To recapitulate what was on the last slide, as an owner of a chip, you can examine that creator code and be confident that you really are the owner of the chip, that the chip is delivering to you the security properties as advertised, that there's no leap of faith. You can see everything that runs before your owner code, and you can be confident that it's initialized the chip as we said. So why don't we then focus on, what exactly is the problem, and the problem is what actually happens when you build the project, and in particular here, like what happens when you build the software for your project. And the first order answer is that you type make all, or name your build system. You invoke this command, and the build system compiles all the code and links it together. But there's a whole bunch of questions you need to ask yourself, when you build. First of which is which compiler runs, which version of that compiler, where did it come from, what other tools run, where did they come from, within the project, what are the dependency relationships between your modules properly maintained, and can you even tell? Does your code depend on any system libraries, headers, or other resources? And how did those get installed? Does every developer have the exact same version installed? What third-party libraries do you depend on? Where did those come from? How do you know? Or how do you know that they're precisely the version that you intended? Does any information about your environment leak into the build? We've all seen, Linux kernel boots, and it names the person who built it, and occasionally it's a funny name and we all snicker at it, but this is really kind of important. Does this information leak into the build, and did you intend it to? And lastly, is your build reproducible? Can two developers working on the project check out the same version, run the build, and get binary identical artifacts? And really, for the purpose of OpenTitan, I think that this last bit is kind of the most important bit. Is, because we're making these guarantees about the security of the chip, and there's the ROM and ROM extension are built from purely from code in our repository. Anybody ought to be able to check out a particular version and run the build and get the binary artifacts that we as creators produced. So, this sort of why does OpenTitan care? And I may have maybe jumped ahead a bit in my bit on the last slide, but we want to basically hermetically build reproducible build artifacts. I'm sorry, I stumbled over the wording on the slide. We want hermetically built reproducible build artifacts precisely because we're building an open source silicon root of trust. We want to be confident that we know exactly what went into the construction of the Mask ROM and the ROM extension. We want auditors to be able to inspect and audit the code in the Mask ROM and the ROM extension. We want them to be able to exactly reproduce the same artifacts that we, as part of the Silicon Creator Group, produce. And as an open source project, these bits of code are the guarantee that the chip has the properties that we say. And just to be clear in this context, when I refer to auditors, I mean professional auditors, like folks that would help you through the certification process, customers of the chip itself, so silicon owners, to use the terminology in one of the prior slides, and members of the open source community. So really, anyone who cares or is interested ought to be able to get the same artifacts that we produce. So let's look at an example of an actual build failure that we experienced in the project. There's an issue that's part of our GitHub that was a real build failure, and the person who discovered this reported in the bug, quote, "I suspect this is a build system dependency error because if I run the command ninja-c, etc., enough times that eventually the build converges, and from there he can run the test command successfully." And the investigation showed that this in fact was an error in the build configuration, where we accidentally omitted a reference to an auto-generated header file that is a dependency to one of the Mask ROM unit modules. So this is kind of it's a simple but I think effective demonstrator of something that can go wrong, and eventual consistency is not really a desirable property in your build system. And to paraphrase the green puppet from a famous film franchise, either you should build or do not build. There's no try again. Although we all know everyone just will try again after they think they've worked out the error. But really, this is kind of a simple but effective demonstration. So let's revisit our problem statement. What should happen when you build your project? The build system should calculate the dependency relationships needed to build whatever it is that you requested. So in this case, where we're talking about the Mask ROM and the ROM extension, when you ask it to build the ROM, it should calculate all the dependency relationships and figure out how to build the thing that you asked for. The build system should know about your project's third-party dependencies and, optionally should be able to go retrieve them on your behalf. This is a bit of philosophy on how you prefer to configure a project. You can also vendor in your third-party dependencies, check them into your project. In my opinion, upgrading the vendor dependencies within your project just kind of creates churn. And if there's a better mechanism, you should use that. The build system should know about the tool chain that's needed to build your project and understand how to run the various components of the tool chain. So, classically, this is compiler configuration, how you set up CC and LD in a makefile, for example. The build system should know how to run any miscellaneous tools that are required by your build. The build system should isolate and redact the peculiarities of your development environment from the build. So like the name of your home directory or where you've put the source code as an example. It's pretty typical for strings like that to end up in the artifacts because they end up like in a debug section or the author uses the file macro in C, for example. And given the same set of inputs, the build system should reproduce the same outputs every single time. So this is kind of what we want. And I think just to clarify on what I mean by additional tooling, if you think about scripts that maybe convert a bin file into a C hex dump that you can include, or something that produces a version.h that has your git hash as part of your version, or if you're running some higher level code than something that's, say, strictly embedded, and you need to use like the protobuf compiler or any other kind of IDL compiler, that's an additional tool. And your build system should know how to deal with those tools. So how do we get there? Well, let's decide what exactly we want. We want an expressive representation of the build rules and the relationships between all the targets. We want dependency management as a directed acyclic graph. You should not have cycles in your dependencies. If you do, there's probably something wrong. You should have a mechanism to query the dependency relationships between your targets, so you can know, what depends on what, and whether or not that those relationships actually make sense. We want the build system to be able to support multiple programming languages and target architectures. Easy integration of additional tools, so either your custom scripts or like things like the protobuf compiler. Easy management of third-party dependencies. There's hermetic builds, which are the build system arranges to invoke whatever tool, whether that's the compiler or even a custom tool, to prevent inclusion of unspecified resources into the target, and reproducible builds. So given the same set of inputs, a binary identical artifact should get produced. So for OpenTitan, we spent a great deal of time examining different build systems that we could possibly use. And we settled on the build system called bazel. Bazel is the open source version of Google's industrial strength build system. Some of you probably have seen the literature that internally Google maintains its own internal source base as a monorepo, and the version of bazel that runs there is capable of dealing with the dependency relationship between millions of files and hundreds of millions of lines of code. It's when I started at Google, I was utterly shocked at how big the source base was. So bazel conceptualizes your project as a directed acyclic graph of targets and dependencies between them. Bazel expresses the build in something called Starlark, which is a Python-like language for writing rules that express the relationship between the targets. Starlark is actually quite a bit more than that. It allows you to define macros, which can help you automate configuration of targets. It also allows you to instantiate your own rules. So if you have a custom tool, you can write a rule that can express the relationship between the inputs and outputs of that rule, of what it is that you're trying to build, and then encode that into the rule. Starlark is sort of designed so that it can be easily parallelized. So a lot of Starlark is construction of what you might call immutable data structures. So bazel understands multiple tool chains, and the rules that talk about building different targets can express which tool chains or target architectures, if you wish, are valid for a specific set of targets. There's a rich set of extensions to support additional tooling, such as protobuf compiler. Writing support for your own extensions is relatively easy once you've internalized a bit of Starlark. Bazel can be told about your third-party dependencies, and it can download them over the net and validate them on your behalf. So this is kind of what I said earlier about not necessarily wanting to check those things into your project. And Bazel sandboxes all tool invocations, whether that's the compiler or a custom tool. So when you build a target, Bazel effectively constructs something like a cheroot and it puts into the file system only the inputs that are listed as dependencies, and the tool itself, to actually do the build. So that might be like the C compiler and its associated binaries. There's a bunch of other things to note about Bazel. It by default it discovers your local compiler toolchain and Python installation, but you can override these so that you can force the build to use a specific toolchain, or you can configure additional toolchains. This toolchain configuration, to be fair, is not exactly trivial, but I think that, at least for me, the difficulty is worth the effort. And then there are several different sandboxing mechanisms within Bazel. So this is most important when it comes to executing tests, and your tests may depend on a local resource like an FPGA board or so forth. So why don't we take a quick look at what the build rules look like. So if you're familiar with make, a rule in make is typically an output its inputs, and then a command line that describes, what tool to invoke and how to invoke it. Bazel abstracts a lot of that into the toolchain configuration, although you can exert fine-grained control over that when you need to. So in this example, I'm showing on the left a CC library, which is either C or C++ library for the UART driver that's part of our Mask ROM. I enumerate what headers are required, what sources are required, and what dependencies this particular target needs. There's a dependency here called UART regs. I'll speak about that in a minute. And then there's this other dependency called, software device lib base, and I have a reference here as to what that refers to, which is in a different part of the project. There's a base library that has a bunch of useful headers and let's call them, it's not precisely the C standard library, but let's say it's our standard library of functions. So when the compiler is building the UART library, it can access any of these header files that are referred to in the base library, and it can access the built output of the sources. So when the project is built, the dependency relationships will be examined. The base library will be built first because it's needed by the UART library. The sources will be compiled and archived into a sub-library, and then that will get further linked when the UART library gets built. So this is kind of the feel of what this looks like. It's kind of like I think of it as these rules are a little bit like functions that describe the target in question. And then let's see, I was going to speak about this UART regs thing. So this is a label. It happens to be, kind of down in the root of the project, which is not precisely the best location for it, but this is an auto-generated header file. And you wouldn't necessarily know that from the rule, or from the label, but basically what this is, just to explain it, is we have within the OpenTitan project, the peripherals all describe their register interfaces in JSON files. And then there's a tool in the project that consumes those JSON files and it emits header files that have all of the pound defines that you would ever deem necessary to interact with that piece of hardware. So within the project, this actually refers to an auto-generated file. The reason it's in the root is because this is from an experiment where I was doing the evaluation of bazel, and I just put it in the root out of expediency. That's not long-term where it's going to end up. So this is, I think, kind of gives a feel about what the build rules look like within bazel. So I also talked about external or third-party dependency management. So a lot of modern open source projects have a lot of third-party package dependencies. And if you think about whatever your favorite language is, they all have package management systems these days, whether that's pip for Python or npm for Node or cargo for Rust. And it's pretty typical to just list your requirements in a file of some sort that the package manager knows how to deal with, and those dependencies will go download, or the package manager will go download the thing that you asked for. But how do you know what you're really getting, and how do you know that the contents are good? I mean, there's been attacks on package management systems, such as the PyPy dependency confusion attack. And if you have a multi-language repository, now you may have sort of an intersection of different dependency management systems. And if you have artifacts that are C or C++, there is no package manager for C and C++. That's kind of manual mode. So Bazel has a concept called the workspace, which really is the root and configuration of your entire project. And the workspace unifies all of this third-party package management into a single system within your project. So all of your third-party dependencies can be specified in the workspace configuration. You can specify them as a Git repo with a label or a hash, a downloadable URI, or even a local file system path. So you might have, some code elsewhere on your local file system. That last bit, the local file system path, is not exactly, reproducible by others. But if you're working on the interactions between two packages, it might be convenient to use it. So when Bazel downloads a package, it will download an archive like a tar file or a zip file, and it will check that archive against a SHA-256 sum before unpacking. And that SHA-256 sum is usually something that's deliberately configured by the person managing the project, rather than, say, taking it on faith that a package manager retrieved the correct SHA-256 sum. So it puts a little bit more work on you as somebody maintaining the code for a project. But I think this is worthwhile because if you're managing a project, you really need to know and be responsible for those things. Bazel rules might exist in a third-party package, or maybe not. It's pretty easy to write rules for projects that or dependencies that don't have them, especially if they're small. And if you need a patch version of a package, you can also apply patches to a package during your workspace initialization. So I think we've all had the experience of, oh, I need this dependency, but I need one extra feature, you either get in the kind of problem of having to apply a patch or work out how to have a local copy or a clone in your GitHub that has the patch in it. Bazel can do that for you. So moving on, one of the things I mentioned in a set of requirements is to be able to understand the dependency relationships between the various targets in your project, and Bazel provides what is effectively a query language to allow you to discover this. So here is the graph of dependencies for the UART driver that is part of the Silicon Creator code within our project. So it depends on this thing called UART regs, which we talked about earlier. And I can then see that depends on this Python script called regtool, and then an input file, which is the JSON, or in our case, HJSON file that contains the register description. So this will get executed during the build to produce the header file that is ultimately needed by the UART package or module. We depend on the base library, which again, we can see the file level dependencies here. We depend on this thing called arch device, which is architectural constants, things like clock rates of the various internal blocks inside the project. There's an error library, which contains a unified set of error return codes. And then, of course, there's the files themselves for the UART driver. And then, all of these things ultimately depend on the C++ toolchain. So this is the kind of thing where you can really easily figure out exactly what does your project depend on, without having to go dig through all the source code and figure that all out. You can also understand the relationship between targets. So you might want to know, in this case, how does the Mask ROM library, which is all of the code for the Mask ROM before we actually link it at its destination address. How does that Mask ROM code depend on this error module that I alluded to earlier, which contains the unified set of error codes? Well, it depends on that by way of the HMAC driver and the UART driver, who both independently depend on the error module. So you can, in addition to just getting a graph of what your dependencies are, you can track down how do those dependencies relate to different targets in your build. I have found this incredibly useful in my time, both at Google in general and specifically within OpenTitan, to understand how things are put together. Let's talk about testing for a moment. Bazel includes test rules that are first-class citizens within the build graph. These rules can be designated test only, which means you can disqualify test only artifacts from anything used in production. So you can avoid accidental inclusion of test artifacts. The test execution itself is sandboxed, so you can make sure your tests only have access to their specified resources. As I alluded to earlier, you can relax this if you need to. The tests can be categorized with tags, and then the query mechanism can be used to select test categories. So you can select lightweight test for a fast continuous integration cycle and heavyweight test for, say, a nightly, just as an example of something you could do. And this is kind of one of my favorite features. The dependency query mechanism can use to find all tests that have a dependency relationship with the files in a changed list, which can then be used to select the relevant set of tests to run for a pre-submit. So rather than running all the tests everywhere in the project, you can use this query mechanism to select only the relevant tests. I think I'm a little bit over time. Should I continue or go faster, or what should I do? I think I'll continue quickly.
You have almost 8 minutes still, yeah.
Okay. So one of the things that Bazel supports is something referred to as air-gapped execution. And this means that Bazel can actually build your project within an air-gapped environment. So on a computer that has no network access at all. Normally, Bazel wants to retrieve all of your dependencies and some of its own dependencies via the network. But your project, like that, might not be appropriate for your project. And in particular for OpenTitan, because we're seeking certification, there's certain portions of the project that need to be built in an offline secure environment. So Bazel can facilitate this by allowing you to perform a preparation step in which it will download and verify all of the external dependencies first. And then you can transport your project repo and all of these prepared archives into the secure environment. And then within the secure environment, Bazel can be instructed to use the pre-prepared archives instead of attempting to download them from the network. So this is a really convenient feature to have. And there are things within that we're still learning about. Bazel is as I said, an industrial strength tool, and even I am not an expert in all of the things that it can do. So a couple things that we're still learning about is that Bazel can generate coverage reports over your code base by executing your tests and using the compiler to measure coverage. Bazel can execute your tests with the various sanitizers enabled. So if you want to run your code with ASAN, MSAN, TSAN enabled, you can do that. We're learning about additional language support. So most of the low-level OpenTitan firmware and tests are in C and C++, and there's a lot of utility scripts in Python. There's some parts of the code base that are written in Rust. This is mostly host-side tooling. Long term, we actually want to write big parts of the firmware in Rust, but we aren't there yet at this stage of the project. So for Rust, cargo is the de facto method for specifying dependencies, but as I alluded to earlier, we really want all of the dependency management under Bazel's supervision, and we want the build of code under Bazel's supervision. I say Bazel because I'm a fan of Monty Python and John Cleese, and I kind of feel like an opportunity was missed to not call it Bazel. But with that aside, so there's an extension for Bazel called cargo raise, which can consume a cargo configuration and emit Bazel rules for all of your dependencies. And long term, we would like the build of the Verilog hardware descriptions to be brought under Bazel's umbrella. And this is kind of still unsolved. There's been a lot of work internal at Google at doing this. And I myself have done a bit of this. I've spent some time a couple of years ago learning about Verilog and FPGA development using Project Ice Storm and Project Trellis. And I find Make to be so distasteful now that I spent the time to write my own toy rules for my toy project. So I'm confident that long-term we can solve this problem in OpenTitan and get the whole project brought under the supervision of Bazel. So to conclude, the OpenTitan projects, we're building an open source silicon root of trust. Our design is compatible with the rigorous requirements for FIPS and common criteria certification. Our code base is public, and we want anyone to be able to build and audit the code. We have many third-party dependencies and a complex build, and we need a build system that is up to the task of expressing the build accurately and exactly. We need that to be able to assist in auditing. We need the build artifacts to be reproducible. We need multi-language support, multi-target support, and support for custom tools. And we need a build system that comprehends testing as part of the overall build or project process. So for us, Bazel fits the bill. And that's all I had. I can take questions.
Thank you, Chris. There are actually 3 questions, but maybe we could take one in the breakout room because of the time. But let me read the first question to you, Chris. It's from Dave. J3101, a hardware protected secure environment, is it compliant?
I am afraid that I don't know the answer to that.
Okay. I think this is not a question, but it's a statement by Dave that the problem statement is also configuration management statement.
I would say that that's effectively correct, that getting the build system set up properly and correctly is a configuration management problem. I think that at least in my experience, Bazel seems to be one of the better tools in this regard. I've really, in my career, have spent a lot of time staring at make files and wondering how the heck things got into a certain state, and where different make variables have come from, and it's something that I think is expressed better in Bazel and is easier to kind of figure out why things happen and how things depend on each other than in other build systems.
Okay. There's one question from Rob, but I would request Rob to take it with you in the breakout room so that we could not delay the next speaker. But thank you, Chris, so much for sharing the insights on OpenTitan project. Really appreciate it. And thank you for being part of hardwear.io as well. Friends, if you have questions and you would like to talk to Chris, please join the breakout room. There will be a pop-up onto your screen right now to interact with our speaker and talk more about his project.
Great, thank you.